So we're going to be doing number 6 of the 2021 AP Calculus BC free response question. So let's get right into it. It says the function g has derivative of all orders for all real numbers. The Maclaurin series for g is given by gx equals that on its interval of convergence. So A, it says state the conditions necessary to use the integral test to determine convergence of the series. That use the integral test to show that series converges. So A, we really don't need any previous information from up here. But remembering the integral test, if we make our series equal to a function, this function must be decreasing, continuous, and positive. So just by looking at e to x, as x increases, the denominator gets bigger, which means the whole fraction decreases. So right, it's continuous because it never undefines itself, and it is always positive no matter the value of x. So we can do the integral test, and the integral test says that we do the limit as the upper bound b approaches infinity. We start at 0 because that is where the series starts. 1 x dx. So now we have to just solve this. This is equal to minus 1 over ex from, oh sorry, this has to be b up here. It can't be infinity. That's why we do the limit. So 0 to b. It is wrong if you put infinity up there. You can't have an integral that goes to infinity. And this is the limit of b goes to infinity. If we evaluate this, keep the limit, and 1 b minus 0. So all this is going to give 1, and if we use the limit here, this is going to go to infinity. It's infinity, which means all this fraction is going to go to 0. So we end up having minus 1, which is 1. And the integral test says if the integral converges, so we'll say int converges, means the series also converges. So we just prove its convergence. So we just a little recap here. We stated the conditions necessary, and we used the integral test to show that it converges. We completed A. Moving on to B now. It says use the limit comparison test with the series, the one we saw before, to show that the series g of 1 that converges absolutely. So we have to remember 2 things, or 3 things here, I guess. First, that converges absolutely means that both the series itself and its absolute value converges. That's what it means to converge absolutely. Second, it's going to be important, I'll show you why later, that every alternating series which terms are decreasing converges. And this always happens, and I'll show you why this is important later. And the third is the limit comparison test, which is when we have 2 series, if we do the limit as n approaches infinity and we divide these 2 series, this will give us a constant c, and if this constant is bigger than 0, then a n and b n either both converge or both diverge or diverge. That these three are important to remember. So if we want to prove that this series converges absolutely, let's analyze the series itself. And by analyzing the series itself, what we get to is that it is a alternating with decreasing terms. Decreasing. Which means that the series itself converges. But to know it converges, so the series itself converges, this is right, but now we have to check the absolute value, and that is what we're going to use the limit comparison test for. So just to write this down, we can erase all this. I'm going to say series does converge, test absolute value with limit comparison. And that is what we're going to do now. So, limit as n goes to an over bn. We're going to set an to the series we know converges. We'll do n here. And bn is the absolute value of the series they gave us. This is equal to 1 over 2e to the n plus 3. Now we just have to do the limit. All this divided. We can just flip the denominator and multiply, which would leave us with this. And as n goes to infinity, 3 is insignificant, and these two, if we divide those two, we get this is all equal to c. 2 is equal to c. And if c, remember, is bigger than 0, this is true, both a and bn either converge or diverge, and we know that 1 over e to the n converges, which means bn also converges. So now we know the absolute value, because that's what we were testing for, remember, the absolute value also converges. And if the series converges, we'll do this with green. If the series converges and the absolute value converges, that means it converges, converges absolutely. And we just proved that, which is what they were asking for. Moving on to C now. So for C, it says determine the radius of convergence of the Maclaurin series for G. So this up here. So for this, we need to use the ratio test. Ratio test. And the ratio test says that the limit as n goes to infinity of the absolute value of an plus 1 an. And it converges, the series converges if L is smaller than 1. If L would be equal to 1, the test would be insignificant. It wouldn't mean anything. And if L is bigger than 1 or infinity, the series diverges. So, getting right into it, an plus 1 would be minus 1, n plus 1, x n plus 1, 2e n plus 1 plus 3. Absolute value of that. We can take out the 1, just leave the x on top. X plus 1, 2e n plus 1 plus 3. So we have the first part of the fraction. The second part would be absolute value of an minus 1 to the n, 2e to the n plus 3. Absolute value of that. That is equal to 1 over 2e to the n. We just take out the alternating 1. That will change between minus 1 and 1. If it's absolute value, it'll always be 1. So we don't need that minus 1. Now we can set up the ratio test. Limit as n goes to infinity of an plus 1 goes on top, so x n plus 1 over 2e n plus 1 plus 3. We can flip the other fraction because they're going to be dividing, and we can just multiply, make our life easier. Plus 3. I just flipped an over here. Oh, it's over 1, so it doesn't really matter. We're checking over. We actually, in an, we missed an x here. See how we had it here and we added 1? We missed an x up here. X to the n. This one is only x to the n. Yeah, this fraction looked way too simple. X to the n. So now we're good. So just by looking at it, we can take these two out. We can multiply as well. Have x times 2e to the n plus 3 all over 2e to the n plus 1 plus 3. Limit as n approaches infinity. This is all equal to L. So with this limit, I'm just gonna, this x, I want to leave it out here. We're just gonna solve in here where the n's are. So 2 limit of n goes to infinity. E to the n times e plus 3. The x is out here. All this is equal to L. So, as n approaches infinity, the 3's here do not matter. They are insignificant because of how big it's going to infinity is. And we can also take these two out. When we take those two out, we don't have n anymore, so the limit also goes away. And we have L is equal to 1 over e times x. So they're asking for the radius of convergence here. They're asking what radius, where does this series converge? And we have to remember that if L is under 1, it converges. So for what values of x will this converge? So if we have the L is equal to x over e, and L converges when it's smaller than 1, we can use this to find our values of with what values of x does this series converge. So yeah, just by solving this, we get the whenever x is smaller than e, which means our radius of convergence is e. And we don't have to prove endpoints of where it converges. We just know that our radius is e. So now that is all they were asking for in C, the radius of convergence. Last one, D. Says the first two terms of the series G1 are used to approximate G of 1. Use the alternating series error bound to determine an upper bound on the error of the approximation. So what we have to remember here is that for the alternating series error bound is that the error, or E, at most will be, we can write that, will be the absolute value of the first neglected term. So what this means is that if we're using the first two terms to approximate a value for G of 1, the first neglected term is the third term. And to remember, so the first, the second, and the third, these are the terms. We'll say T. The n values start at 0, so 0, 1, 2. So if we have the general, we have the general equation for it. So we just have to put in n equals 2 to find our third term. And we say the error is at most the absolute value of that, which is -1 n to 2. Remember, this is important. N is not 3, it is 2. 2e to the 2 plus 3. We can simplify this a bit. 1, 2e. 2 plus 3, but that's basically it. That is at most the error, and yeah, that is number 6 of the 2021 AP Calculus BC free response questions.